In this video, we're gonna go over limits at infinity. And so we have been working with just taking limits as x approaches a number. Now remember, infinity is not a number, it's just a concept that things go on forever. So as f of x becomes arbitrarily close to a finite number L, for sufficiently large and positive x, we write the limit as x goes to infinity of f of x equals L. And so I have some graphs here to kind of illustrate, and then as it goes to negative infinity as well. So if as x goes to infinity and you get a number, so like in this case, as x goes to infinity, the y values are approaching this horizontal line L, then we say that that is a horizontal asymptote. And as x goes to negative infinity, right, so as x gets arbitrarily large on the negative side, negative infinity, and if it equals a number, that limit, so in this case, the limit is m is the horizontal asymptote. Oftentimes they'll be the same. They'll just be one horizontal asymptote, but in this case, this kind of looks like the graph of inverse tangent of x, so we have two horizontal asymptotes as x goes to positive infinity and then as x goes to negative infinity. So let's evaluate these limits. What happens as x goes to negative infinity of 1 over x? And then what happens as x goes to infinity of x squared? And what about as x goes to negative infinity of x squared, and so on? So let's look at 1 over x. How do we find that limit as x goes to negative infinity? So one way we can do it, if we don't know the graph, is we can do a table of values. And so I'm going to have x and 1 over x. As x goes to negative infinity, that means we want to get large on the negative side. So like, let's say negative 100, negative 1,000, negative 10,000. So what happens when you do this? So notice that this then will be 1 over x will be negative 1 over 100. X equals 1,000 will be negative 1 over 1,000, and so on, negative 1 over 10,000. And notice that these are very, very small numbers. This is going to be, what is negative 1 over 100 in decimal points? Negative 0.01, right? And then negative 1 over 1,000 is negative 0.001, 1/1000th, and then negative 0.0001. So notice that they keep getting closer and closer and closer to 0, right? The bigger we get on the negative side, so if this is negative 1,000,000, we're going to be even closer to 0. So therefore, I can say the limit as x goes to negative infinity of 1 over x approaches 0. And we can do the same thing as, let me add in here, the limit as x goes to positive infinity of 1 over x is also going to be 0. Just get rid of the negatives and we are doing the same math. So it's going to get, as x gets large, arbitrarily large, or 1 over x, our function goes to 0. And then if you look at the graph of 1 over x, this graph looks like this. So this is our graph of 1 over x. And so we can see that as x goes to positive infinity, notice that what are the y values doing? The y values are getting close to 0. They're never equal to 0. They just get close to 0 because notice that 0 is not in the domain of this function. And then as x goes towards negative infinity, the values also get close to 0. And so y equals 0 is a horizontal asymptote for 1 over x. So oftentimes you may be asked, determine if a function has horizontal asymptotes. So that means find the limit as x goes to positive infinity and as x goes towards negative infinity. What happens for y equals x squared? So I have the limit as x goes to infinity and negative infinity of our function is x squared. So notice that as x goes to infinity, you can probably think of the graph. This is also going to go to infinity. But if you do a table of values, right, if you're not sure, being going to infinity means getting arbitrarily large. So if you square these values, 10 square is 100, 1,000 square, very large, 1 million square, very, very, very large. So this is going to go to infinity as x goes to infinity. And what happens as x goes towards negative infinity? So if you put negatives in here, now our negatives are going to get square, right? So if I have 10, negative 10, so let me say as x goes towards negative infinity, so this is going to be negative 10 square, which is going to be positive 100. And then negative 1,000 will be negative 1,000 squared. So that's going to be a positive number. So this is also going to go towards positive infinity as x goes towards negative infinity because of the square. And looking at the graph, we can see that as well. So here's our graph. So as x goes to positive infinity, the y values are going towards positive infinity. And as x goes towards negative infinity, the y values are going towards positive infinity. So the limit is infinity in both cases here. Now what about for e to the x? Let me copy this one. This one we can look at the graph right away, or you can also do a table of values. So I guess let me be consistent and stick with the table of values. So let's do as x goes to positive infinity first. So as x goes to positive infinity, what's happening? So again, going towards positive infinity means you're getting arbitrarily large. So this will be e to the 10, e to the 100, e to the 1,000. At some point your calculator is going to give you an error because there's just too many digits. But remember, e is 2.718281828459045. So if you put this to the 10th power, so almost 3, right? 2.7, so you can round it to 3. So 3 to the 10th, I mean, 3 squared is 9. 3 to the 4th is 81. So 3 to the 10th is going to be really, really big. So this is already a large number, e to the 100, e to the 1,000. So the y values are going to go to infinity as x goes to infinity. What happens as x goes towards negative infinity? So we're going to try negative 10, negative 100. So e to the minus 10, what does that mean? A negative exponent means it really belongs in the denominator, right? So this is 1 over e to the 10. Now here we said e to the 10 is a huge number. So what's 1 over e to the 10? So that's going to be very small, right? And then here you have e to the negative 100. So that means 1 over e to the 100. E to the 100 is even larger. So 1 over that is going to be very, very small. So this is going to go to 0. So our y's go to 0 as x goes towards negative infinity. And let's look at the graph of e to the x. So here's our graph of e to the x. And as you can see, as x goes towards positive infinity, right, as x gets arbitrarily large, the y values are also going towards positive infinity. They're also getting arbitrarily large. As x goes towards negative infinity, our y values are getting close to 0. They're never 0, but they get really, really close to 0. So does e to the x have a horizontal asymptote? Yes, right? We have a y equals 0 is a horizontal asymptote. Did y equals x squared have a horizontal asymptote? No, right? They go both sides. As x goes to infinity, y goes to infinity. As x goes towards negative infinity, y goes to positive infinity. So this does not have a horizontal asymptote. To have a horizontal asymptote, you your limit as x goes to positive or negative infinity has to be a number. That number is your horizontal asymptote. Polynomial functions are the ones that are essentially not going to have horizontal asymptotes. So here's something that is an odd power function. So this is y equals x cubed, but a lot of odd power functions will have this behavior where they, as x goes to infinity, 4y equals x cubed, notice that y goes to infinity. As x goes towards negative infinity, the y values go towards negative infinity. So we say the limit as x goes to positive infinity of x cubed is infinity, and the limit as x goes to negative infinity of x cubed is negative infinity. So there's no horizontal asymptotes because these are not numbers. This is the graph of a quadratic, but it could be to the fourth, to the sixth. They're going to have similar behavior. They're either going to go up or it's going to be flipped. So here, in this case, both limits, so as x goes to plus or minus infinity of x squared, they go to positive infinity. So as x goes to infinity, y goes to infinity. And the odd power functions will have this behavior. They'll be going to the opposite infinities. So we want to look at rational functions. So determine the end behavior for the following rational functions. So for the first one, part A, f of x equals x over x plus 1. So I can see right away I do have a vertical asymptote, or at least x equals negative 1 is not in the domain. So we may have a horizontal asymptote. So let's see. How do I figure out the horizontal asymptote if there is one? So I want to look at the limit as x goes to plus or minus infinity of my function. And so usually we split it up. So the limit as x goes to infinity of x over x plus 1. So there are two ways to do this, the long way and then the cheap and easy way. So let me show you the long way so that you can appreciate the cheap and easy way. So the long way, and properly called the long way, requires long division. When can we do long division? When you have a rational function, right, made up of polynomial in the numerator and polynomial in the denominator, and when the power on the numerator is greater than or equal to the power in the denominator. So here they're equal, so I can do long division. So the way we're going to do our long division is, what do I do? So it's x divided by x plus 1, right? So then I'm going to set it up as our little division box, and then the numerator goes on the inside of the box and our divisor, the denominator, goes on the outside of the box. And so I ask myself, what do I multiply x by to get x? And that will be 1. So I offset it, and then you multiply. So 1 times x is x, 1 times 1 is 1, and then just like as with any division, we subtract. So these cancel, distribute that negative, that becomes a minus. So those cancel and I'm left with minus 1. Now I can keep going. This has a degree of 1, that has a degree of 0, so I can't continue. So I can say x over x plus 1 is really equal to the quotient, so 1 plus the remainder. So plus negative 1 over x plus 1. That's how we write the remainder. So now when I'm taking my limit, the limit as x goes to infinity of x over x plus 1, I can say this is the limit as x goes to infinity of 1 minus 1 over x plus 1. Now, as x goes to infinity, right, this means x is getting arbitrarily large. So you're going to have a large number over here. 1 over a large number is going to go to 0. This is essentially our 1 over x limit, right? The limit as x goes to infinity of 1 over x is 0. 1 over x plus 1 is just shifted over, but that's still going to go to 0, and so we're just going to be left with 1. So our limit here is 1. because you're going to have, as x goes to infinity, you have a constant, so that constant remains, and that goes to 0. So my limit is 1. So that is the long way. And then as x goes to negative infinity, we can do the same thing, because that is going to go to 0 as well. So we are going to have a horizontal asymptote here of 1. Now the cheap and easy way is, as I take the limit as x goes to infinity of x over x plus 1, we identify the highest power in the denominator. Once you've identified the highest power term in the denominator, you divide by that term. So divide every term by that highest power. So what that means, I am going to identify in the denominator I have x. X to the first is the highest term that I see. So I'm going to take that term, just the x term, and divide every single term in my expression by that. So what that's going to look like is the limit as x goes to infinity of x over x divided by, and then in the denominator, the same thing. So I'm going to do x and then divide by x plus 1 divided by x. So you identify the highest term in the denominator and then divide every term by it. And so then simplify. So this becomes the limit as x goes to infinity of x over x is 1, x over x is 1 plus 1 over x. And now I use the limit that we found above, right? The limit as x goes to infinity of 1 over x, that goes to 0. So you're left with just 1 over 1, which is 1. Therefore, the limit is 1, so we get the same exact thing as we did the long way. It's just a faster way of doing it, that long division. So, for example, in this one, I don't really want to do long division on a 4th degree polynomial, but you can try it just to practice your long division. So what we're going to do is I'm going to say, what is the limit as x goes to infinity of 15x to the 4th minus 7x plus 1 over 5x to the 4th plus 8x cubed minus 8. So following my steps from above, I'm going to identify the highest power term in the denominator, ignoring the coefficient. I guess I should have said that. So at the denominator, I have x to the 4th, x to the 3rd, and a constant term, degree 0. So x to the 4th is my highest x term in the denominator. So then we're going to divide everything by x to the 4th. So I'm going to have the limit as x goes to infinity, 15x to the 4th divided by x to the 4th minus 7x divided by x to the 4th plus 1 divided by x to the 4th. And we're going to do the same thing in the denominator. So I have my 5x to the 4th plus 8x cubed minus 8, and I'm dividing each of those by x to the 4th. So this is instead of doing long division. So simplify this, limit as x goes to infinity, x to the 4th of x to the 4th, that's just 1, so I get 15 minus 7x over x to the 4th is 7 over x cubed. Use your rules of exponents there. You divide the same base, you subtract exponents, all over 5 plus 8 over x minus 8 over x to the 3rd. Now, as x goes to infinity or negative infinity, anything that has an x in the denominator, what's going to happen to that? What happens to these guys? X is getting arbitrarily large, so think 100, 1,000, 10,000, 1 million. What is 7 over 1 million cubed? That's going to go to 0. What's 1 over 1 million to the 4th? That's going to go to 0. And so on. So anytime there's 0 in an x in the denominator, and you're going to infinity or negative infinity, that's going to go to 0. So we're left with 15 over 5, which is 3. So that means that g of x has a horizontal asymptote at what kind of value is this? It's a y value, right? It's the limit as x goes to infinity. So we're looking at what are the y values doing. So we have a horizontal asymptote at y equals 3. And notice that I can do the same exact work as x goes to negative infinity, so it's a full horizontal asymptote instead of a half horizontal asymptote. What I mean by that is like 1 over x, y equals 0 is a full horizontal asymptote, meaning as x goes to positive infinity and as x goes to negative infinity, the limit is 0. For e to the x, we have as x goes to negative infinity. It's still a horizontal asymptote, but I just say a full horizontal asymptote when both positive and negative infinity go to 0. I don't think that is an actual official math terminology. This is just Professor Owens' math terminology. Full asymptote and half asymptote. Don't really quote me on that, but just when I say a full asymptote, that means that as x goes to plus or minus infinity, the limit is the same. I will do 2 more examples of this, but I'll break up my video so it's not too long. So in the next video, on part 2, I'll do part C's and D of this example.